Good evening, folks. If you remember back to the first semester, there were two ways to approach a Newton's second law problem. There was the formal approach, which had a protocol to it and which always worked, but was fairly lengthy in its presentation. And there was the quick and dirty approach, which took about 30 seconds, and if you really understood what you were doing, was definitely the way to go. It, unfortunately, though, required you to really kind of understand what was going on with the problem. Turns out that electrical circuits are kind of the same way. There is a formal approach to attacking a circuit. It's related to what's called Kirchoff's laws, which you'll learn about shortly. And there is what I call the seat of the pants approach, which is a very informal way of attacking a problem. And it requires you to just kind of think about what you've been given and look to see what information you have available to you, and you just kind of pick away at the problem. And so this video is designed to give you an example of a situation in which a problem is being attacked using this seat of the pants approach. So the upside of using this approach is that if you get good at using the tools, you can analyze circuit problems pretty quickly. The downside is that you actually have to understand the tools pretty well, and in some instances you have to be kind of clever. You have to be able to look at a problem and just sort of think outside the box. And a lot of people, that's just hard to do. In any case, I'm going to go through the tools that are available to you to do this kind of thing. You're going to get a chance to see them in action in a problem. And then at the end, we'll go ahead and review what the tools were once again. To begin with, any kind of meters in the circuit, ammeters, voltmeters, they're only there to identify places in the circuit of interest. Okay, they're not needed for the actual analysis. Therefore, you need to redraw the circuit without them to make the circuit less cluttered. If you can come up with the equivalent resistance for the entire circuit, the current drawn from the battery will equal the voltage associated with the battery, the terminal voltage, divided by that equivalent resistance. The voltage drop across resistors in parallel is the same. Resistors in series share the same current, and you can add them up to come up with a single resistor that will take the place of the whole crowd. Current into a node will equal the current out of a node. Each branch has its own current. For a given voltage, the current through a small resistor is going to be big. The current through a large resistor is going to be small. This, I might add, is an inverse relationship, which is to say if you have a resistor that's twice the resistance of another, it will have half the current. Again, assuming that the voltage across the elements is the same in both instances. You want to simplify circuits wherever you get the chance. The voltage difference between one side of a resistor and another is equal to the current passing through the resistor times the resistance of the resistor. Additionally, the voltage across a resistor drops if you're moving in the direction of the current flow. And lastly, all roads lead to current. And if you want to know what that means, stop the video and you can read all of this, or you can simply continue on through the video. I'm going to end up animating all of these ideas, and at the end we're going to go through and I'll review each one of these points piece by piece. So here is our circuit. We've got resistors. We have a voltmeter across this resistor. We have an ammeter through this little section. We have a certain amount of current coming in here. I'm not showing you the power source that's providing that current, but I am letting you know that 4 amps is coming in here. We're going to go from there. So the first thing you want to do with a circuit like this is get rid of the meters. You don't need them. All that the meters are doing is letting you know that at some point in time you're going to want to know how much current's flowing through this section, and you're going to want to know what the voltage is across that resistor. That's all the meters are doing. So we can get rid of them. And here's the circuit without the meters. Now once you've done that, you might wonder what you're going to do with these sections as far as current flow goes. And in fact, you can simplify this circuit. You don't have to actually do it, although I'm going to show you what it would look like if you did. What's important to note is that the voltage at this point and the voltage at this point are essentially the same voltages. Voltage is potential energy per unit charge. It's an energy-related quantity. So a charge carrier that moves along this path is essentially going to lose practically no energy at all. Wires have very little resistance to them, which means they take out very little energy as charge moves through them. So from an energy standpoint, from a voltage standpoint, this point and this point are essentially the same points, and this point and this point are essentially the same points. That means I could slide this point over, and I could slide this point over, and I would end up with the circuit looking like this. Doing this would help me identify the currents, because as you can see, each branch has to have its own current, and if you couple that with the fact that each resistor in a series combination is going to have the same current passing through it, you can see that this current is going to end up going all the way from there to there. This current will go from there to there. This current will go from there to there. We have just defined all of our currents. And if we go back to the original setup, you can see that this current corresponds to this current corresponds to this, and this current corresponds to this. As I said, simplifying is the key. So in this particular case, you have 3 resistors in series. We'd like to combine them. We can do that by realizing that these resistors are in series, and the equivalent resistance of a series combination just adds the resistors. So with that information, we can redraw this section as a single resistor whose resistance is the equivalent resistance. I'll call that R7. Notice that we're using the tools that I mentioned earlier. Okay, so what else can we do? Well, we could take this resistor and this resistor, which are in parallel, and we could combine them to make one resistor that will do the job of the two. Our equivalent for a parallel combination is embodied in this relationship. You put in the numbers, here's what our equivalent is, and you can redraw this combination of resistors in the circuit as a single resistor whose resistance is our equivalent. Now you have a new current flowing. It's essentially going to be the sum of R3 and R4. So I just mentioned that I5 was going to equal I3 plus I4, but what is it in terms of the 4 amps that's coming in and the I2's worth of amps coming out through this 120 ohm resistor? Well, it turns out that the current coming into a node, where this node is this junction here, is going to end up equaling the current coming out of that node. Using that information, it just makes sense that I5 is going to end up equaling the 4 amps coming in minus the I2's worth of current that ends up going through the other branch. And putting that information onto the schematic leaves us with this. So now it's time to try to figure out some of the other currents. So one of the other tools you have is the fact that resistors in parallel, this resistor is in parallel with this one, will have the same voltage drop across them. And you know the voltage drop across a resistor is equal to the current through the resistor times the size of the resistor. So here we go. Voltage across resistor 2, which I'm calling V2, equals the voltage across resistor 8, which I'm calling V8. These are really delta V's, although they usually aren't written that way. So you just need to be aware this is actually a voltage difference across the resistor. Using IR, we can write this. I5 is the current going through here. R8 is the resistor, the equivalent resistance. Here I'm substituting in for I5. Here I'm distributing the R sub 8. Here I'm pulling the I2 R sub 8 over onto the left side. Here I'm pulling the I2s out. Here I'm dividing by the R2 plus R8, bringing it down, putting in the numbers, and coming up with I2 equaling 0.1 amps. The information of which I place dutifully into my circuit. So now I want to go back to my original circuit with these parallel resistors in place because I'm interested in determining I3 and I4. And the tool that I'm going to use now has to do with whether the resistance is small or large in this parallel combination. And the current through large resistors is going to be small, so the current through this larger resistor will be relatively small. Small resistance is going to be having large current, large resistance is going to have small current. And the bigness and the smallness is going to be related to one another. They're going to be proportional. And the largeness and smallness, there's going to be a ratio. So let's think about it. You got 4 amps coming into node B. 1/10 of an amp comes out of node B and goes to the 120 ohm resistor, which means 3.9 amps continues on. Why 3.9 amps? Because 4 comes in and 1/10 comes out this way. The rest has to go this way. My 40 ohm resistor is twice as big as my 20 ohm resistor, which means my 40 ohm resistor ought to have half the current that my 20 ohm resistor has. Put a little differently, if we split the current that was coming between B and C into 3 pieces, one of those pieces would go this way and 2 of them would go this way, so that this way would have twice the current that this was having. Doing the math, I3 is going to be 1/3 of the 3.9 amps that goes between B and C, which is 1.3 amps. I4 is going to be 2/3 of the 3.9 amps that go between B and C, which is going to be 2.6 amps. So what else do we need to know about? We need to know what's going on with the voltmeter, which is across the 120 ohm resistor. We know the voltage across the 120 ohm resistor is the current through it times the size of the resistance. We do that math, we come up with 12 volts. We'd like to know what's going on with the ammeter, which was located between B and C. We already determined that that's 3.9 amps, so that's what the ammeter would read. The voltage drops across the various resistors would require Ohm's law. I'm going to do it for R4. So here's V equals IR. Here are the numbers placed. Turns out that the voltage across R4 apparently was 26 volts. If we wanted the power dissipated across any of the elements, again, I'm going to do it for R4. Power dissipated by a resistor is determined using I squared R, put in the numbers, apparently it's 67.6 watts. And that pretty much does the problem and brings us back to that last tool, which is to say all roads lead to current. And I want to say a little bit more about that now. So you want voltage across a resistor, you have to figure out the current through the resistor so you can multiply by the resistance to get the voltage. You also have to do this if you happen to have a voltmeter across the resistor and you want to know what the voltmeter was reading. You want an ammeter reading, you have to figure out the current through the branch. You want to know how much power is dissipated by a resistor, you have to figure out how much current there is passing through the resistor. You have to square that quantity and multiply by the size of the resistor. You want to know how much power is provided by a power supply. You have to figure out what the current is being drawn from the power supply, and you have to multiply that quantity by the terminal voltage. In other words, just about any kind of problem that you're going to be asked to do is going to require you to figure out how much current is passing through the branch that's associated with the element that you're interested in. All roads lead to current. So, the seat of the pants approach to analyzing electrical circuits, it's powerful. It requires that you understand the tools, though, which is not a bad thing because understanding the tools means that you understand how electrical circuits work. This is something you want to strive for. Anyway, that's it.